When we are training larger models, we are using the supercomputer. Oak Ridge Leadership Computing Facility, which is a DOE Office of Science user facility, hosts two of the fastest supercomputer, which is Frontier and Summit. Together, these computers provide about 2.2 quintillion plotting operations. It's an incomprehensibly large number of calculations.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring the many ways we can harness the power of artificial intelligence to learn more about our world. I'm also in a personal quest to discover if AI is going to be more of a help or more of a hindrance to our work as geoscientists. Last episode, we spoke with some fascinating solutions architects at NVIDIA who are pushing the limits of hardware that supports AI programming. Today, we're examining the infrastructure and computing power of supercomputers. With their amazing processing power and speed, supercomputers are enabling scientists to tackle complex problems and simulate phenomena that were previously unimaginable. When paired with AI, we're significantly increasing our ability to analyze and apply the vast amounts of Earth observation data and insights for tackling real-world problems. These advancements are pretty exciting, but as we explore the intersection of these two technologies, we're raising important questions about the future of computing and the role of human intelligence in an increasingly automated world. Are we building a real-life deep thought or HAL 9000? Let's dive into the conversation to find out. This episode of Down to Earth is brought to you by the Geoscience and Remote Sensing Society's technical committees. As part of the world's leading professional association for the advancement of technology, the GRSS technical committees are innovation hubs, bringing together experts from around the world to forward cutting-edge geoscience research, development, and applications. To learn more and be part of the premier community driving the future of geoscience and remote sensing, visit grss-ieee.org and join a technical committee today.
So I spend a great deal of my time thinking about how to make AI work for science, helping communities around the world in anticipating, analyzing, mitigating, and responding to disasters. Of course, I don't do this alone. I'm surrounded by a team of very smart people with expertise coming from all different disciplines.
This is Dr. Dalton Lunga. He's a research scientist and a group leader at Oak Ridge National Laboratory in the United States. In these roles, he leads and directs a scientific research portfolio that combines AI, high-performance computing, and Earth observation data to address national security challenges.
So my team and I are building GeoAI tools for supporting decision makers, emergency responders with near real-time insights that are derived from Earth observation data and other data sources, where we are leveraging the automation component to come up with robust and scalable AI and computer vision techniques that are being deployed on the supercomputing resources.
At the Oak Ridge National Laboratory, Dalton gets to work with two incredible supercomputers. Summit, which was built in 2018, and Frontier, the world's fastest supercomputer in 2022. Using these two supercomputers, Dalton and his team are training and implementing large GeoAI models for addressing disaster response in near real time. Let's learn more. So I want to start with a few definitions so we're on the same page for this discussion. First of all, what is GeoAI?
GeoAI is a research area that is growing within the geoscience and remote sensing community. I can say it is an emerging focus area that is seeking to advance AI methods to address geospatial problems. We call it GeoAI to emphasize the aspects or characteristics of geospatial data sets that are otherwise very challenging and limiting for existing AI tools. I mean, there's a limited amount of AI tools that can handle spatial temporal data sets. That alone was enough of a motivation for us to ask, how best can we come up or develop AI tools that is spatially aware, that incorporates location information? How do we scale such methods? Who do we bring to the table to build such tools.
Yeah, geospatial datasets are definitely unique forms of data. So it makes sense to me that we specifically focus on GeoAI. What are some of the exciting areas where scientists are applying GeoAI systems?
Our colleagues here at the lab have made huge breakthroughs in advancing AI for extreme event detection and building climate models, large foundation models for climate. In other applications, we are supporting population distribution estimation at scale with the GeoAI tools that we are creating. So that's helping to reduce an otherwise effort that would have required sending people on the ground to do census collection. In some cases, there are parts of different countries that are unreachable and accessible, meaning that segments of the population will be unaccounted for. But by leveraging using AI, Earth observation in high performance computing environments, we are able to support and uncover some of these missing people and putting them back on the map.
It's really exciting to hear all the ways we can apply GeoAI systems. And it's super important to be able to generate results in near real time when it comes to natural disasters. Now, it's obviously all a work in progress right now. So, what are some of the challenges or limitations when it comes to developing these systems?
So first, I can say for any scientific problem-solving approach, there is always limitations. Some are known, some are yet to be discovered. So GeoAI systems have their own share of limitations. The research is still in its early stages. It depends on a rapidly evolving set of technologies, including, of course, AI, remote sensing technologies, the data that we are currently using that is being collected. It's coming in large volumes. The scientific challenges that we are working on is becoming complex on a daily basis. Take, for example, the need for effective emergence planning, all the way from preparedness, response, and recovery to address the impacts that are due to the high frequency, high intense duration of natural disasters. That requires AI that can respond almost in near real time and adapt to any disaster event without the need for retraining. Today, we don't have such AI, GeoAI systems. Part of the challenge is that the data comes in all sorts of forms. Some of the forms are well aligned with existing methods so that we can quickly just deploy the existing tools. But in most cases, the new situations fall into what we call out of distribution cases, meaning we almost need to retrain our models to fit the conditions of the new data forms. Another challenge is the type of GeoAI that the community is looking at building. We want to be able to build digital assistants for crisis management. That is going to require that we train AI models, GeoAI models, AI models that learn from multiple databases, data types that are different. That turns into what we call a multimodal learning. We don't have effective GeoAI techniques to handle multimodal data integration. It's a hard problem. We need lots of data, much bigger models, and how to align the different modalities. We don't know yet. So training from different contexts that captures different real world scenarios, even though it promises a lot of breakthroughs, getting to enable that is a big challenge. This is why I'm so excited about the large GeoAI foundation models that the communities are rallying to build and the promise that these models are going to bring, to different facets of these problems.
You mentioned large GeoAI foundation models. What exactly do you mean when you say large here?
Right. So we look at the number of parameters of the model as a quantifying metric. And how to get the largest model you can find also depends on other things, including the amount of data that is available to pre-train the model and how generic the model is and being adapted for other tasks. For example, we are learning that by scaling the amount of data, we can also increase the number of parameters, sort of confirming to what's called the scaling laws that allows for such models to start showing capabilities of being applicable to tasks that are novel. For example, with the large language models, people started to notice that even though the models were trained to predict missing words in a sentence, The same models could also be used in writing software and doing other reasoning tasks. That's what is called emergent abilities coming out of these large foundation models. So the largest geospatial and climate foundation models that is out there, at least to the best of my knowledge, is a 3 billion parameter model for high resolution satellite imagery, and Orbit, a 113 billion parameter climate foundation model. Both of these were trained by our teams. The high resolution satellite imagery was trained by my team, and then the Orbit, the climate prediction model, by my colleagues. We are currently testing these models, but there are additional tests that are being conducted before these models can be pushed out to the open source for other communities to use. The value of these models becomes evident when one fine-tunes and deploys them in an application space. So that depends on the availability of data, the labels to fine-tune the models, and also the computing resources to be able to do the fine-tuning. For example, for a 113 billion parameter, I mean, it's unthinkable that you'd be able to actually fine-tune it on a laptop.
Right. I mean, ideally, at some point, we'll be able to scale these models for the average user who doesn't have the supercomputer in their lab, but we're not there yet. So, the Oak Ridge based foundation model for Earth system predictability, otherwise known as Orbit, is an advanced vision transformer model that scales up to 113 billion parameters. That's a ton of parameters, and training this model must have been intense. Can you tell us a bit about how GeoAI models are trained?
Okay, training large foundation models requires a combination of different steps, starting with the pre-training dataset. So we spend a lot of time creating pre-training datasets so that the diversity is enough to allow for model generalization, because that's where you see the benefit of GeoAI tools. When models are now able to work in new situations and removing the human, from doing the labeling. So on how we actually train the foundation models depends on other factors like the model size, how big is the training data, and how much compute resources are available, and what type of hardware is one using. For example, we use PyTorch. I know some colleagues that are using TensorFlow. And then we set up the required ingredients, including choosing your hyperparameters, model size, learning rates. And then depending on the size of the model, we need to select the optimization scheme. Are we doing model parallel? That is, are we slicing the model and sending different parts of it to different GPUs, to different nodes? Are we doing data parallel? We keep the full model in one GPU, which in most cases is limiting, because if you are training at 3 billion parameter scale model, that's not going to fit in a single GPU that we have. 113 billion parameter model that was trained for climate prediction, there's no way you'd fit that even across 4 GPUs, let alone when you start to push in the data to train the model. So we need to come up with these strategies. So how the model then goes on to learn is informed by what we call a pretext task objective. So currently there are 2 common choices that the community is using. One is called the masked modeling. That is, you teach the model to fill in the gaps of missing. So you intentionally remove parts of your data. So for example, let's say you're looking at a picture and then you randomly remove pixels, and then you guide the model to fill in the missing pixels. So that is reconstructing the missing pixels. And the second approach is based on what is called contrastive learning. In this case, the model trains by contrasting samples against each other so that it can learn things that are similar as belonging to the same class, and then attributes that sets different classes apart. So in a way, you want to pull things that are similar together as you're learning, and then things that are different, you would like to push those apart. Once all of this is set, we can run our software in a distributed manner to start training the model. Usually it's a babysitting process because at times things fail and we have to restart many times. Turn the knob to get the right settings, get the training going again. And for larger models, the process is compute intensive. The pre-training takes longer to converge. this requires a lot of support, from your HPC support teams and engineers to help accelerate, the computations. Because the other thing that we need to pay attention to is the energy consumption costs. However, once you have a trained model, that can now be leveraged in fine-tuning, in supporting, in creating value to the applications. And that can be done on other resources, computing clusters that have enough memory, to be able to do the required iterations for the fine-tuning process.
I have so many questions. First, you mentioned HPC or high performance computing, and I want to define that for our listeners. So, can you tell us what high performance computing is?
So that's a process that combines a lot of computing resources to solve complex science problems. In other words, I can describe this using supercomputing, which is powerful and advanced computers that help to perform complex calculations and simulations that otherwise we would not be able to do if we were to use, for example, my laptop. These systems are designed with high-speed interconnections, links between them. They come with a lot of resources in terms of storage. You're able to handle a lot of data, performing calculations at very high speeds. So that's what we mean by high-performance computing, in particular supercomputing.
And in your laboratory, what equipment do you use to perform high performance computing?
So we use both small computing clusters with 4 GPUs or 8 GPUs. But for the most, when we are training larger models, we are using the supercomputer. So the larger geospatial foundation and larger climate prediction models, these are being trained on Frontier and Summit. Together, these computers provide about 2.2 quintillion floating operations. So you can think of quintillion as a million trillion or a billion, whichever you choose. It's an incomprehensibly large number of calculations.
Wow. Okay, let's back up because that's definitely a hard number to wrap my brain around. Okay, if we compare the supercomputer like Frontier or Summit to an average human brain, what are we looking at? How many people would make up a supercomputer?
So the answer to this will surprise you. At least it did surprise me.
Up next, we'll reveal the surprising answer to this big question. Plus, we're diving deep into evaluating large GeoAI models. And most importantly, we ask just how helpful these powerful supercomputers are when it comes to AI and geoscience, especially when we consider the resources they use. All this right after the break.
Want to be at the forefront of geoscience and remote sensing innovation? Then join one of the Geoscience and Remote Sensing Society's technical committees. With 8 committees to choose from, you'll find your niche. From earth science, informatics to data fusion and climate technologies, our committees are driving progress and advancing the state-of-the-art in geoscience remote sensing work. Through our networks, you'll collaborate with global professionals, participate in cutting-edge research, and apply innovations to real-world challenges. Enhance your career, expand your network, and contribute to a better tomorrow. Visit grss-ieee.org and join a technical committee today.
Welcome back. Today we're speaking to Dr. Dalton Lunga, Senior R&D Scientist and GeoAI Group Leader at Oak Ridge National Laboratory. In our conversation so far, we've explored the potential of large GeoAI foundation models and the incredible number of parameters that supercomputers like Frontier and Summit are capable of processing, which together provide the ability to complete about 2.2 quintillion floating operations. Before the break, I asked Dalton to break down that crazy number by comparing the power of a supercomputer to the power of the human brain. This is what he had to say.
The human brain and supercomputers have many differences, including their size, power consumption, and processing power. The comparison is not going to be an apples to apples. It's going to be an apples to oranges comparison. First, the human brain is small, while the supercomputer, for example, Frontier, is thousands of square feet larger. On power consumption, the human brain is super efficient. It uses about, I think, 20 watts of power, while on the other hand, Frontier requires tens of megawatts to run, and it consumes a lot of resources to cool. So here is a surprising part. Turns out the human brain can perform about 1 quintillion of operations per second, which is the same as Frontier.
Did you get that, listeners? Our brain performs the same number of operations as Frontier. How is that even possible? Either way, I'll take it. But of course, Dalton had more to add.
The brain and the supercomputer differ in how they process information. On the supercomputer, for example, Frontier, you have much larger storage than what you have on the brain. On the other hand, the human brain is pretty effective at compressing and storing world representations in compact forms and very efficient at retrieving information once it's stored. So for supercomputers, since these are engineered systems, we can easily link them toward a common goal to solve bigger and complex problems faster and more precisely. I think it's much tougher to get humans to work together on bigger problems. I mean, look at how the world is disagreeing on the climate change threats. If we pose that challenge to Frontier and connect with other supercomputers, we can have some progress in that while the humans are disagreeing. And also, Frontier can perform tasks around the clock without needing to sleep.
Yeah, the fact that we need to sleep makes us a little less efficient than Frontier. But wow, I never knew our brain was as capable as a supercomputer. That's really cool. I'm curious though, how long does a supercomputer stay viable hardware-wise?
I would say 5 to 7 years. Summit was installed in 2018, for example, and was available and open for science experiments for about 5 to 6 years. I think Frontier will also be available for this same timeline, or maybe more, I don't know. With the rapid development of new hardware, these estimates could change. Also, each time a different hardware is called upon to build the system, we don't just use the same hardware all the time. Actually, very soon, hardware vendors will be bidding to build the next supercomputer after Frontier.
Every 5 years? Wow. I guess that's pretty reflective of how quickly AI hardware and software is changing. And what about the carbon footprint of these supercomputers? I understand your team is thinking about ways to reduce this.
Absolutely. So we are not yet there, but energy efficiency is already a major topic. There is a huge need for us to develop adaptable, power-conscious AI systems. If we succeed as a community, the outcomes will have tremendous impacts on reducing carbon footprint and also adding to the sustainable practices of AI through energy efficient algorithms. And in other parts, these could inform new ways of doing science.
That's good to hear. Now, I wanted to shift focus to discuss evaluating large GeoAI models. What are some of the best practices your team's been following?
This is an extremely important topic. This is where it's also crucial to have collaborations. So, in my opinion, we cannot have best practices coming from the same teams that are designing the tools. The teams can be part of an evaluation process, but they need to collaborate. We need to collaborate with, have independent groups that can critique our work, both for good outcomes, good benefits out of the models, and also for bad outcomes. So this requires establishing commonly agreed upon benchmarks, right, and protocols to run the evaluations. Given that we don't have this in the community again, the geospatial foundation models that are coming out, there is a huge gap. So the easy part is building internal data sets for different applications I mentioned, testing the models, and then we deploy them. However, when you start to evaluate things like bias, the potential harms, threats, when the models are being adapted by others, we just don't know how to do that yet. So that is a big question that requires we come together as a community and try to find ways. I know in the large language models and the people that are developing those tools, there's been greater talk of coming up with what's called red teaming. That is, you can have opposing teams that, in a way, are not part of designing these tools, but they create test cases to try to explore, kind of like, you can think of it as hacking the models to expose its limitations. So maybe that's something that within the geoscience and remote sensing community, we can start to rally around.
That's a neat idea. Another thing that comes to my mind is the importance of data-centric AI approaches here, especially when pre-training these big GeoAI models. A huge part of the success when evaluating a model depends on the quality of data it's working with.
Yes, that's correct. The GeoAI tools are data-driven. How we build the data is crucial. The training process, it's part of teaching the machines how to mimic humans in finding useful patterns from which insights can then be used to derive, actionable decisions. So having a balanced and diversified training data allows for models to train and generalize to new situations. A lot of the information can easily be derived from the AI models and the data products. So by diversifying during training, data construction not only increases the generalizability of the models, but we can also be intentional, right, of being inclusive in the representation of the users that are otherwise going to be impacted by these tools. So being inclusive allows for us to start to identify potential problematic use cases early. And it could also help us with the evaluation strategies before we can have these models deployed at large scales.
Mm-hmm. And in your view, why are national laboratories like the Oak Ridge National Laboratory best positioned to develop large GeoAI models for the community?
So we are a federally funded open science and research organization. And as such, we have high levels of transparency across our collaborations and the work that we do. We are not biased by profit interests in the work that we do. Having access to supercomputing resources allows us to think at problems of today and tomorrow at scales and complexities that surpass anywhere else. Apart from the computing resources, we have access to vast amounts of data sets, both Earth observation data and simulations data, that can allow us to build much larger models, both for Earth and environmental sciences. So we are well positioned to really build these tools that can allow for larger impacts in scientific discovery. We talked about benchmarks and evaluations. That is also another potential benefit where I see national labs playing a huge role, being independent evaluators of tools that could be coming either from industry or academia.
That makes sense. And just quickly, the resources of the Oak Ridge National Laboratory are available publicly, right?
Absolutely. Oak Ridge National Laboratory is an open science lab. We support the open source and open science community. We publish our scientific breakthroughs. So we've started to release GeoAI datasets that we've created, and these are available already. We have software repositories that we share to support advancing research with the communities. For example, my team is working in supporting the SpaceNet challenges by developing baseline codes that the communities will then adapt, in advancing their solutions. So this is how technology has always advanced throughout history, by sharing information. However, I should highlight that given that AI is a dual purpose technology, especially powerful AI, in the form of these highly capable foundation models, we have to exercise a greater level of responsibility. That is to make sure that as we advance AI for all the good use cases, to support different communities, scientists, to do scientific discovery and help impact some of the complex challenges that societies are facing. At the same time, we need to think about how do we restrict access so that those with bad intentions are not going to take the same tools and repurpose those for very, very bad outcomes. So that requires starting to think about putting more checks, evaluations. So the delay in releasing the models is informed by this gap that we are trying to close, given that as a community, we don't have a lot of benchmarks and test cases to really understand and critique our models to establish what are some of the limiting factors. So we need to have these guardrails that we can deploy. And if we can come together as a community, to put some of these benchmarks, I think in the future, it's going to be quicker for some of the tools that we are developing to make these available for use, to the communities, because they would have been evaluated, critiqued, and benchmarked on commonly agreed test cases and metrics.
Well, I hope we get those evaluations and benchmarks in place soon. Now, this season, we're exploring the exciting opportunities and important challenges that need to be addressed to ensure AI in geoscience and Earth observation is ethical and sustainable. And this exploration stems from a global conversation about whether AI will be a boon or a bane for humanity. What are your thoughts? Do you think AI will be more of a help or a hindrance in our field and industry?
I think it is both. The examples that we discussed demonstrate a set of clear positive impacts that can arise due to AI. For example, accelerating the data transformation and decision during crisis management. That's a great demonstration of where AI has been of help to make sure that we stay in tune with the daily changes that are happening and helping communities that are affected by disasters. On the other hand, how we build AI and use it could be a hindrance if we do not incorporate the guardrails and protocols to protect the potential outcomes that may arise. Some of the best practices that are needed here to make sure that there's a shared understanding and some level of literacy around how AI is changing the geoscience data ecosystem. Also understanding the opportunities that are being presented, the challenges and the potential threats. The lack of representation and inclusion could be a major issue because a huge swath of the population, if left out, they could potentially be on the receiving end where we can start to see high levels of inequalities being perpetuated by AI, either because the policies that are existing are being continued silently by some of these models and algorithms that are being developed, or the data that is being used to create the models is leaving out these communities to start with. So that could obviously hinder progress on any form of sustainable development effort that is being put in place to support all communities across the world.
They say, with great power comes great responsibilities. With such capability to process and analyze data and models, supercomputers today are poised to help solve many of the questions scientists have, especially in the field of GeoAI. Understanding how our Earth works is no simple task because ultimately, the goal of science is to build knowledge. This is why innovation is so important as well. Dalton and his team at the Oak Ridge National Laboratory have an incredible role in shaping the way we use these powerful technologies responsibly and ethically. The outcomes of what they do and the impacts of the work they have done will certainly help define the path forward to what's next for supercomputing. So when it comes to my question of whether AI will be more of a help or a hindrance in geoscience work, I'm feeling that AI will definitely be more of a help as long as we know how to properly and responsibly scale our work. You can connect with and follow Dr. Dalton Lunga on LinkedIn. Also, visit geoai.ornl.gov to learn about the exciting work he's doing with his team at the Oak Ridge National Laboratory. In our next episode, we're shifting gears from training supercomputers to training the masterminds using them. So be sure to follow us on Spotify and Apple Podcasts so you don't miss out. And go check out our sponsors at IEEE_GRSS on X and Instagram and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Manil Maski and Fabio Pacifici for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.